Precipitation. So precipitation is the opposite of something dissolving. Right? We can better understand precipitation reactions by looking at the reaction quotient Q. That guy again. Remember, Q is very related to the equilibrium constant K. KSP is the value at equilibrium only. Q calculated exactly the same way, but at any state, any combination of concentrations. So if Q is equal to KSP, then it's at equilibrium. That means the solution has as much dissolved in it as it can, and so additional solid will not dissolve. If Q is less than K, that means the solution is unsaturated and more can dissolve. So if Q is smaller and needs to get bigger, how do we make it bigger? We increase these concentrations. Those are the product concentrations. So Q is going to move in the direction it's going to go towards K, because K is equilibrium. That's the final destination. If Q is smaller, it needs to go up to match K. These guys need to go increase and more will dissolve. If Q is greater than K, then these things are too big and they have to come down, and that will cause this equilibrium to shift to the left, and solid will precipitate out of solution, usually. So we can use Q to predict whether a precipitation reaction will occur when two solutions are mixed. First, we need to identify the potential precipitate, and then we need to calculate Q and compare it to KSP. So in Chem 1A, we would look at, the combination of these two ions, and if the product was insoluble, we say a precipitation will happen. Well, now we know that everything is at least slightly soluble, and so whether it precipitates or not is going to depend on the concentration of those solutions. A solution containing lead 2 nitrate is mixed with one containing sodium bromide to form a solution that is 0.06 molar in lead nitrate and 0.0158 molar in sodium bromide. Does a precipitate form in the newly mixed solution? So that's a lot of words. It's actually worded in a way that's easier than it could be. They could say, well, there's this many milliliters of this concentration of lead nitrate is mixed with this many milliliters of this concentration of sodium bromide. Is it going to precipitate? And then we'd have to do some dilution problems and add some things together, and it would be kind of confusing. So they did all of that for us. They're saying that in this newly mixed solution, you've got 0.06 molar of this and 0.0158 molar of that. So what's the possible precipitate? Will sodium nitrate precipitate? No. Sodium, potassium, lithium, and ammonium are the top row of the solubility rules. They are always soluble, no exceptions. Nitrate is right up there as well as one of the anions along with acetate that's always soluble. If you didn't remember that, you could look at sodium and nitrate and go looking for its KSP, and you would find out that it's ginormous. Here, the big clue that we're supposed to look at the other one is that we're given the KSP for PbBr2. So that's what we're going to look at. And the solubility product constant, we're always looking at it dissolving. So PbBr2, that's going to be in equilibrium with Pb2 plus and 2Br. We've got our KSP. we could do a whole ice table here, but we don't need to. What we need to do is calculate Q. Q is the same type of calculation as K. It just doesn't have to be at equilibrium. So when this is first mixed, what's the concentration of lead? 0.06. Again, you gotta be a little bit careful. This one has 1 lead per unit, so it's the same. If we were looking at the nitrate, we'd have to multiply by 2. And the bromide, what's its initial concentration? 0.0158. So let's do that calculation, 0.0600 and 0.0158 squared. .498 times 10 to the minus 5. So when this gets to equilibrium, Q has to equal KSP. Is it currently bigger or smaller than KSP? It's bigger, right? Q is bigger than KSP. So that means that this reaction is going to proceed in a direction that's going to make these concentrations lower. How does it do that? By making precipitate. In order for Q to become equal to KSP, the reaction has to shift to the left, has to form more solid. That's the precipitate. So does it precipitate? Yes. Any questions? Yeah. Any other questions? Q is greater than KSP, yes. Selective precipitation is where we're going to precipitate one of the ions and not the others. We're going to be selective about what precipitates. And so we're going to choose a reagent to precipitate whatever ion that is based on KSP values. So we're going to choose something that is not very soluble with the cation we're trying to precipitate. We want to have differences in KSP values of at least 1,000, factor of 1,000. And then we can figure out the concentration needed to begin or trigger the precipitation by looking at Q and KSP. A solution contains equal concentrations of barium, lead-2, and calcium ions. When potassium sulfate is added to this solution, which cation precipitates first? Hint, see table 18.2. I can't answer this question without looking at solubility product constants. Well, there it is. What are the things that could possibly precipitate here? We've got potassium sulfate, right? So it's going to be barium sulfate, lead sulfate, or calcium sulfate. Barium sulfate, lead sulfate, calcium sulfate. Let's look up their KSP values. Here's barium sulfate and calcium sulfate and lead-2 sulfate. Is the most soluble one going to precipitate or the least soluble? The least soluble. So what I'm looking for is who has the smallest KSP. It's going to be barium, right? This is the smallest one. So as we add potassium sulfate, the barium ions are going to precipitate first, because they're going to reach that saturation point soonest. And then who's going to precipitate next? The lead, because this is the next smallest. So next the lead will start to precipitate, and then at the end the calcium will start to precipitate. We can't do a complete separation of all three of these ions. But what we can do is we can add enough sulfate to get just to the point where the lead is about to precipitate. And then we can filter out the solid. The solid is the barium sulfate. And so we can separate that out from the rest of it. Yeah? Why would we do it?
Yeah. Well, what was the question?
Well, the question is which cation will precipitate first. So it'll be the barium. And then I just added a whole bunch of stuff. Okay, finding the minimum required reagent concentration for selective precipitation. So we've got a solution with magnesium and calcium ions, and we're given their concentrations. And we're told that they can be separated by selective precipitation with potassium hydroxide. We're asked what minimum hydroxide concentration triggers the precipitation of the magnesium ion. So what we want to look at is the precipitation of magnesium, and we're going to write it backwards. We're going to write it as dissolving, right? So the magnesium hydroxide, that dissolves into magnesium ions and 2 hydroxide ions. We don't have to identify which one precipitates first because it told us. But if we look at the KSPs, we see that this is a smaller KSP than that one, and so that's why the magnesium precipitates first. So KSP for that magnesium hydroxide, bless you, is the concentration of magnesium times what? The hydroxide squared. So this will begin to precipitate when these concentrations match up with KSP. So we know what the magnesium ion concentration is. It's 0.025. Actually, let's do it this way. And we know what KSP is. So here's our KSP, 2.06 times 10 to the minus 13. And that's going to equal the magnesium ion concentration, which we were told 0.025 times the hydroxide ion concentration squared. So we can calculate the hydroxide ion concentration at the point where this is saturated in magnesium hydroxide. And then you add just a teeny tiny bit more and we start precipitating. So when they're talking about triggering the precipitation or starting the precipitation, we're calculating the equilibrium amounts. So you can use a solver here, or we can divide this side by 0.025. Take the square root of both sides. Two 0.8705 times 10 to the minus 6. .9 times 10 to the minus 6 molar. As we add potassium hydroxide, when the hydroxide ion concentration reaches 2.9 times 10 to the minus 6 molar, we are teetering on the edge of precipitating the magnesium. When we add more magnesium, we'll precipitate out of solution. Any questions?
I understand the calculation, but I did not
The
understand concept.
The concept? Okay, that's very fair. Understands the calculation, but the concept is iffy. So we have a solution with magnesium ions and calcium ions. And one is more soluble than the other. So we see from their KSPs that calcium hydroxide is more soluble than magnesium hydroxide. This solution did not originally have hydroxide in it. It was maybe magnesium nitrate and calcium nitrate or something like that. But as we add hydroxide, we can get a precipitation reaction. We have magnesium in the solution. As we add hydroxide, we can have, because this equilibrium goes both ways, we can have magnesium hydroxide solid be formed. Well, we know what the concentration of magnesium is 0.025 molar. If we add, one ion of hydroxide, is that going to precipitate? No, it's not. If we add 5 gazillion of this, is it going to precipitate? Yeah, sure. All the magnesium is going to precipitate then. But also probably all the calcium is going to precipitate. So what they're asking us is, what is the minimum concentration where we're just going to start getting the magnesium to precipitate? And that point is the equilibrium value for this equation. That's going to be, what we're looking for here is where Q is equal to KSP. When we go higher in these concentrations, then Q gets bigger than KSP and precipitation happens. Does that help?
Yeah.
Anybody else? Yeah.
You said that with one, it won't precipitate. Why?
Pardon me? Oh, if one hydroxide.
Yeah.
So if we had one hydroxide, or like 0.0001 molar hydroxide ion present, we could calculate Q for that. Q would be 0.025, the magnesium concentration, times this really, really, really small hydroxide ion concentration. Well, when we do that calculation, we're going to find out that Q is smaller than KSP. Okay? Q is going to move in the direction of KSP, and it will get equal to that if it can. So in order for us to get our Q to be equal to KSP, we can't change that because that was fixed. We add more hydroxide. And at the point where it's just going to start precipitating is where Q is equal to KSP. Great question. Any other questions? So 2.9. We can also look at what are the concentrations of the ions that are left in the solution after selective precipitation. So this solution has lead 2 ion and silver ion, and we're asked two questions. Let's just look at the first one. If selective precipitation is to be achieved using sodium chloride, what minimum concentration of sodium chloride do you need to begin to precipitate the ion that precipitates first? Which ion precipitates first? Lead or silver? Silver. It has the smallest KSP. The silver is going to precipitate first. So let's write the equation for silver. So when silver dissolves, silver chloride dissolves, it makes silver ions and chloride ions. And we're looking for the minimum concentration of sodium chloride. So we want Q to be equal to KSP. That's where it's going to begin to precipitate. And that's calculated using the concentration of the ions in solution. So we know what KSP is. It's 1.77 times 10 to the minus 10. We know what the silver concentration is, 0.025. And we're trying to figure out what the chloride ion concentration is. So the chloride ion concentration is going to be 1.77 times 10 to the minus 10 divided by 0.025. 7.08 times 10 to the minus 9. That's the chloride ion concentration. What's the sodium chloride concentration? It's not a trick question, the same. Sodium is one of those spectator ions here. And sometimes we identify the spectator and include them. A lot of times we ignore them and leave them out. But we have to become okay with bringing them in and out. So as we add sodium chloride and get to this concentration, at this point, Q for this reaction is equal to KSP, and we will be teetering on the edge of silver chloride precipitating. Everybody okay with that? What is the concentration of each ion left in solution at the point where the second ion begins to precipitate? So that's the answer to part A. Moving on to part B. Well, the second ion is lead. And so we want to know the concentration of each ion, so that includes, we're going to need the sodium chloride concentration as well. But we're going to look at KSP for PbCl2. So when that precipitates, Q will be equal to KSP. And KSP is lead concentration times the chloride ion concentration squared. So the KSP there is 1.77 times 10 to the minus 5. That's going to equal the lead concentration, which they had to tell us, 0.085, times the chloride ion concentration squared. So we're going to get the square root do you see what I did wrong there? For lead, it's 1.17, and this is 1.77. That's awfully picky, isn't it? It matters. Let's fix that. Okay. Square root of 1.17 times 10 to the minus 5 divided by 0.085. So the point at which the chloride ion concentrate, the point at which the lead would begin to precipitate is when the chloride ion concentration is 1.173 times 10 to the minus 2 molar. So that's going to be the sodium chloride concentration. At that point where we're just teetering on the edge of precipitating lead, what's the lead concentration? We haven't precipitated any of it yet. It's going to be the same as this, right? So at that point, the lead concentration is the same as the original, 0.085 molar. It hasn't precipitated yet. What's the silver ion concentration? Well, 0 because we precipitated it. That's a reasonable answer. But is it actually all the way to 0, or is it just really small? It's just really small. And we're doing all these times 10 to the minus 30 and stuff, so, we're writing out the really small. It is going to be very close to 0. Well, how do we find it? Well, this is our new chloride ion concentration. And we have KSP for the silver. And so now what we're going to do is we're going to put the chloride ion concentration in here and calculate the silver ion concentration. So 1.77 times 10 to the minus 10 is equal to the silver ion concentration. And our chloride ion concentration is this one that we just calculated. So there's the lead ion concentration and the silver ion concentration. Is this a small number? Yeah, it is. That's smaller than the concentration of hydrogen ions in water. It's a small number. Yes?
Why the concentration of lead stay the same?
That's an excellent question. Why did the concentration of lead stay the same? We calculated the chloride ion concentration at equilibrium for that lead ion concentration. So we're talking about beginning to precipitate. It hasn't started yet. When the chloride ion concentration gets to this point, the solution will be saturated in lead chloride, and if we add more, the lead will precipitate, but it hasn't precipitated yet. Does that make sense? Kind of? Yeah? You sure? Anybody else? You know, we kind of get the feeling with all these calculations that is it actually possible to completely separate things? Not really. It just comes down to, well, how much do you need it separated? Do you need it separated enough that you can't tell it's there anymore? Oh, we can do that. But can we get rid of every last silver ion? No, we can't. So 7.1 times 10 to the minus 9 for the first answer. 1.5 times 10 to the minus 8 for the silver, and 0.085 for the lead.